In the last video, we noted that there were some parallels between the way that you approach solving a linear system of equations and the way that you would approach solving a differential equation. And in particular, we solved this example, y double prime plus 4y prime plus 3y equals 1. And we found that we got this very general solution that consisted of a linear combination of two homogeneous solutions. We have c1, which is some constant, times e to the minus x, plus c2 times e to the negative 3x. And then we had this particular solution, 1/3. And c1 and c2 can take on any values, and you could easily see that if you took the derivatives, it would satisfy that equation. So what we have here is a non-unique solution. There are many different solutions that satisfy this equation. Now that might seem a little strange to you, given that these types of equations are usually constructed to describe physical systems. Now, if I were to run an experiment, maybe I hung a mass from a spring and pulled the mass down and let it go, I would expect to get the same result every time if I set things up the same way every time, right? So you'd expect in a physical system to get one solution, and here we have actually an infinite number. So what gives? Well, we've left out some information here that is usually present when you're running an experiment. In an experiment, you specify the initial state of the system. So in our example that I just mentioned of having maybe a mass hanging from a string, what we have to do is we have to specify where is the mass when I let it go and how fast is it moving. Once that information is determined, then you have a unique experiment and you get the same result every time. But if I pulled the mass down different distances or threw it with different speeds to start out, I would get different answers. And so that is what we need here. We need an initial condition. We need some information about the value of y and maybe some of its derivative in order to get a unique solution here. So let me add to this problem a little bit. Let's suppose that we know that the initial position is y of 0 is going to be equal to 1, and that the initial velocity, the rate of change, is going to be 0. Let's see if we can now solve for the solution to that equation. All right, so the way to do that is simply plug the values of x and y that we've observed in and try to come up with a system of equations for the constants c1 and c2. So we'll plug in x equals 0, y equals 1, and we will get, let's see, 1 equals c1 times e to the 0 plus c2 e to the 0 plus 1/3. And we could write that as 2/3 equals c1 plus c2. And we plug in a piece of information. We're going to need to do a little work there because that's the derivative. So y prime is equal to negative c1 e to the negative x minus 3 c2 e to the negative 3x. And so when x equals 0 and y prime equals 0, we have 0 equals negative c1 e to the 0 minus 3c2 e to the 0 again, which is negative c1 minus 3c2. Okay, so we have two equations. And we'll put a 0 down there. And we have two unknowns, which suggests that there should be a unique combination c1 and c2 that satisfies this initial condition, which is the initial position and the initial velocity if we're thinking about this as a motion problem. Okay, so then we could use our techniques from linear algebra to solve. We'll do that on the next page. We had c1 plus c2 equals 2/3 minus c1 minus 3c2 equals 0. If we were to say add those equations together, we would have minus 2c2 equals 2/3. So c2 must be equal to negative 1/3. And c1 must be equal to, if we look at that first equation, we could bring a c2 over to the other side. And we'll have that c1 must be equal to 1. So our solution is actually e to the negative x minus 1/3 e to the negative 3x plus 1/3. Okay, so that is our unique solution to this differential equation with initial conditions, or what you might call an initial value problem. Okay, so in your homework, which I'll introduce in the next video, you will be asked to solve a couple of these initial value problems with a little bit of guidance. So be prepared to try to reproduce this sort of method.